All right, we're going to tackle one of the most fundamental rules in all of physics. I mean, this is a law that governs literally everything, from that cup of coffee on your desk all the way to the ultimate fate of the universe itself. So let's just dive right in. We're talking about the second law of thermodynamics.
It all kicks off with a really simple observation, something you've seen 1,000 times. Why does a hot cup of coffee in a cool room always cool down? I mean, without fail. And why does it never ever do the reverse? Why doesn't it just spontaneously suck heat out of the cool air and get hotter? It seems kind of obvious, right? But the why behind it? Well, that's where things get really deep.
So here's the weird part. The first law of thermodynamics, the one that says energy can't be created or destroyed, it actually has no problem with the coffee getting hotter. Seriously. As long as the energy the room loses is the same as the energy the coffee gains, the first law is totally cool with it. But we know that just doesn't happen. It never happens. So the first law tells us the books are balanced, but it can't explain why everything in nature seems to flow in only one direction, like it's on a one-way street. And that idea, that one-way flow, is exactly what we need to unpack first. It's all about energy's one-way street. Okay, so this is where the second law of thermodynamics finally steps in. It's the missing piece of the whole puzzle. It's the law that says, nope, processes only happen in a certain direction. It's what gives energy transfer its arrow of time, the thing that forces heat to flow from hot to cold, and makes things go from orderly to, well, disorderly. And look, the implications here are they're huge. This isn't just about your coffee getting cold. The second law tells us the direction of any natural process. It introduces this wild idea that energy has quality, not just quantity. We'll get more into that later. It's also how we figure out the absolute best-case scenario for engines in power plants. It basically sets the ultimate speed limit for them. It even defines what perfection would look like in this world. Right, so this law is so fundamental, a lot of people call it nature's toughest, most unbreakable rule. And that brings us to a really practical problem it creates for anything that we use to generate power. This is what we call the engine problem. It's all about limits and waste. Okay, so to get this, let's think about heat engines. Like in your car or at a giant power plant. They all work the same basic way. First, they get heat from something really hot, like burning fuel. Then they turn a chunk of that heat into useful work, making the car move. But, and this is the absolute key part, they have to dump the rest of that heat as waste into something colder, like the air around us. They're basically just riding that natural downhill flow of heat from hot to cold to get some work done along the way. And if you want to see just how strict this rule is, just look at the engine in a typical car. It's only about 25% efficient. Let that sink in. That means for every gallon of gas you pay for, a staggering 75% of its energy is just gone, poof, dumped into the air as useless heat. And this isn't because engineers are bad at their jobs. It's a hard limit baked into the universe by the second law. Now, there's a formal name for this, the Kelvin-Planck statement. All it really says is that it is impossible, like really impossible, for any engine to just take heat from one place and turn it all into work. Bottom line, a 100% efficient engine can't exist. You always, always have to have that exhaust pipe. You have to dump some waste heat. Okay, so we get work by letting heat flow downhill, from hot to cold. But what about the other way? Can we force heat to go uphill? Can we make it flow against its natural direction? Well, yes, we can. And that brings us to refrigerators, how we actually reverse the flow. We absolutely can make heat move from a cold spot to a warm spot. But there's no free lunch here. The second law says, sure, you can do that, but you have to pay for it. And that payment comes in the form of energy, usually work. This is literally what your refrigerator is doing in your kitchen right now. And yep, you guessed it, this has its own formal rule too, the Clausius statement. It just says that you can't build a machine that does nothing but move heat from a cold thing to a hot thing. To put it simply, your fridge doesn't work if it's not plugged in, right? That electricity from the wall, that's the price you're paying to make heat go the wrong way. And here's something that's actually pretty cool. A refrigerator and a heat pump, they're the exact same device, the exact same technology. It's just a matter of what you care about. With a fridge, you want to cool the inside, so you pump heat out. With a heat pump, you want to warm your house, so you pump heat in. It's the same machine, just depends on whether you're standing on the inside or the outside. So, we know 100% efficiency is impossible, and we know reversing heat flow costs energy. This all leads to a really fundamental question. What is the best we can possibly do? What's the absolute limit? That brings us to something called the Carnot cycle. I love this quote because it just nails it. A heat engine without an exhaust is like a river without a downstream. The flow stops. That's it, right there. You need that colder place, that downstream, to dump the waste heat. If you don't have it, the whole process just grinds to a halt. And that, in a nutshell, is why a so-called perpetual motion machine of the second kind is a complete fantasy. So, to figure out that ultimate limit, physicists dreamed up this perfect theoretical idea called the Carnot cycle. Now, you can't go out and buy one. It's not a real engine. It's more of a thought experiment. It's this flawless, totally reversible cycle that acts as the ultimate benchmark. It's the speed limit for efficiency. No real engine, I don't care how brilliant your engineers are, can ever be better than a Carnot engine running between the same two temperatures. And what's amazing is how simple that ultimate limit is. For any real engine, its efficiency is all about the messy details of how much heat it actually moves around. But for that perfect, ideal Carnot engine, its maximum possible efficiency depends on only two things: the temperature of the hot source and the temperature of the cold sink. That's it. It's an unbreakable ceiling set by physics itself. But why? Why is it all about temperature? Why does that set the limit? Well, answering that question leads us to maybe the most profound idea to come out of the second law, and that's our final big concept here: the quality of energy. So get this. It turns out not all energy is created equal. The first law says a joule is a joule. The second law comes along and says, not so fast. It reveals that energy has quality. A bunch of heat energy that's at a really high temperature is way more useful, it has a much higher quality, a higher potential to do work, than the exact same amount of energy at a low, lukewarm temperature. And I absolutely love this analogy. Okay, who has more friends? You've got Yuki with 10 fun-time friends. That's quantity. Then you've got Kieran with 5 super reliable friends. That's quality. In the universe of thermodynamics, the second law says Kieran is winning. That high temperature energy is like a reliable friend. It's just more valuable because it can actually get more useful stuff done for you. So let's put all the pieces together. What does this all mean? We've got heat that only flows one way, from hot to cold. We have engines that are doomed to be inefficient. And we have this idea that useful energy is always degrading, always going from high quality to low quality. All of this points to a single, pretty inescapable conclusion about the universe. You see, when you look at the big picture, the second law dictates the direction of the entire universe. All that useful, concentrated, high-quality energy is constantly spreading out, evening out, and becoming less useful, lower-quality heat. The universe as a whole is trending towards a state of, well, greater disorder. Scientists call it maximum entropy. So, I'll leave you with this. What does this unbreakable rule, this cosmic one-way street, this arrow of time, what does it ultimately mean for us?